Thanks. I'll begin. Dear Heavenly Father, we thank you for this day. Thank you for these students and this opportunity we have just to meet together and study your creation. Pray that we'd understand a little bit more about it today, Lord. In your name I pray. Amen. Okay, so, excuse me. I have graded your test. I'll give it back to you at the end. It's in terms of the solution that we looked at the other day. I know that the first problem, there was a mistake in the solution. I'll try to fix that and post the corrected solution when I have a chance, hopefully soon. Just want to go through a few more examples of conservation of angular momentum and the study of torque. And then we'll move on to our next topic, which of course is gravitation. And so basically, in the study of angular momentum and torque, well, it's a lot like the linear case, right? But here's an example. Difference, of course, being that mass is replaced by inertia, right? And that's one of the big ideas. So we're supposed to find the final angular. This is from lecture. Where was I? I think 29. Oh, 28. This is lecture 28, actually. So find the final angular velocity, of a pendulum made of a rod of length L and mass m if you let it go from 90 degrees. So you got this. Oh man, where's my ruler? Oh, I'll have to make one. So the idea is, roughly speaking, you let it go. Like, what's the final angular velocity of the end of the marker after you just let it? I can't ideally. I mean, my hand should be fixed rigidly, right? And it just swings like that. But that's the question. So how do you figure this out? What's making it swing down? Gravity, right? Gravity is producing a torque on the system is the way we want to think about this. And so what we're going to do is we're going to study the center of mass. That's where we think about the force being placed. So we think about the gravity acting on the center of mass. The moment of inertia here is 1/3 ml squared. Excuse me. We're releasing it from rest, so our initial angular speed is 0. And here's how we think about it. It's a conservative process, so the initial energy should be equal to the final energy. The initial energy, we have 0 rotational kinetic energy. And I'm setting the potential energy to be 0 where we started. So 0 potential energy, 0 kinetic energy. At the end, we have some negative potential energy, right? And some positive kinetic energy. And so this is equal to 0. So I can solve for omega f here, and I get this. Well, let me scoot down a bit here. There it is. And that minus makes sense because yf is also minus. So it's minus gives you plus. And in particular, you see why I have to use L over 2 is because if you think about, this is a concept that I haven't said too much about, and I don't guess I've derived in here, but it's a matter of principle. If you're dealing with some extended body and you want to consider the gravitational potential energy for it, what you should do is think about the center of mass of the object, and you can think about it having gravitational potential. Consider it as if it was a point particle at the center of mass. In this case, the center of mass swings from y equals 0 down to minus L over 2. It's at half the height. You see, some of the mass on the pendulum, when it swings down to its, when the pendulum goes, I say pendulum, but I mean the stick. When the stick is like this, right? Technically, this, if I was to imagine this little bit of dm up here, still has a little bit of potential energy, 0, right? Whereas down here, you have what? If this is dm, this dm has the little bit of potential energy, what? Minus dm, that's the mass of it, g times L. Because this is distance L, right? And it's complicated. Like, the further down you are, the more negative potential energy your little bit of mass has, right? So if you wanted to think about that bit by bit, you do an integration, right? But you don't want to do an integration, right? You'd rather have like a macroscopic concept to solve this problem. And that macroscopic concept is to consider this whole thing as if it's a point at the center. That's its center of mass. And so the center of mass is in the middle, and that's at L over 2. And that's why I put minus L over 2 right here, because that's the final y of the center of mass. And so there you go. The final speed would be 3g over L square root. Excuse me. A lot going on in this example, right? Rotational kinetic energy, the center of mass concept, moment of inertia of a uniform rod, about the end point as opposed to center. Lots of goodness in this problem, or badness, depending on your viewing. Any questions? Go ahead. Sure. Oh, yeah, it's example 4 on page 3 of lecture 28. Yeah, sure. You'll excuse me, I must partake in a delicious coffee caramel candy. Yes, sir.
If we would get the same answer if we made the initial height L over 2 and made zero height.
I suppose. So you're like, this is y equals L over 2. And that is y equals to 0.
Yeah.
That's interesting. Yes, of course. You have this freedom to adjust the potential energy to be 0 wherever you want. Your ability to do that is actually evidence of what's called a gauge freedom. To every gauge freedom, there's an attached symmetry. And that is actually what modern physics is all about. It's weird that I can say something that deep about our ability to adjust a constant, isn't it? But that freedom actually turns out to be a very interesting story in the big picture of things. This example gives me fits. I don't know, it's not that complicated, but you just follow along. So you got a rigid rod, like I just had over here, right? And you release it from a horizontal position, right? Let it drop. Can't do it. So actually it's the same thing I just did a second ago, right? But this is a different question. This time we're supposed to find the angular acceleration of the rod, right? And also find the force on the pivot point. Now I can assure you that there's a force that's required for me to keep this here like that, right? And even when I let it drop, I still have to keep a force here, which is part of what makes it hard to let it drop, because I have to keep a force there but let it swing. So it's like, if I do too much, that's too much friction. I can't let it, like swing down. There's no friction in this pivot point per se. It's like you could imagine a bolt sliding smoothly along some aperture or something, like whatever. Okay, so how do you solve this problem? Well, it's a combination of torque, gravity, the simple kind, mg. Don't worry, we'll do better before the day's done. And so let's just look at it. So, and we're supposed to find the we're trying to find the angular acceleration and the force just after it's let go. Just after I let it go and start swinging down, all right? At the initial moment of the drop. So for a very small positive time, past time 0. So to find the angular acceleration, at this time, you need to identify the torques that are involved, right? So basically, the torque is coming from gravity. You think about gravity acting on the center of mass of the system. The center of mass is the halfway point again. So you got mg acting here. The pivot arm, though, is L over 2. So the torque produced is mgl over 2, and I'm taking clockwise as positive in this example. All right? So that's your torque. Now, what's the moment of inertia? Well, it's 1/3 ml L squared. We just mentioned that a minute ago here. So this is the rotational Newton's second law, right? I times alpha is equal to the torque, or in this case, torque is equal to I alpha. So there it is. And we get the angular acceleration is 3g divided by 2L. That's the right kind of thing. That's going to be a radians per second squared. Units of length are canceling. It leaves you with radians because of our nomenclature. So there's your angular acceleration. How do you figure out the force? So again, this was the rotational Newton's second law. So to find the force at the pivot point, you got to think about Newton's second law, right? At the pivot point, what's the couple things. First of all, man, let me draw a picture. I didn't draw a picture. Oh. So if you think about this, what are the forces that are on this? Well, you can think about mg like that, right? You've got Fa like this, right? The force at the place where it's pivoting. Are there any other forces on the thing? I don't think so, right? So that's the net force, right? So what I have is, like I said, the mass times the tangential acceleration is equal to what? Now the tangential acceleration is what? Like I said, tangential, right? It's just straight down. So if I take that as positive, mg is positive, right? And I have minus Fa. That's Newton's second law applied to the pivoting ruler. All right? So there's that. By the way, the centripetal acceleration is 0 because at the initial starting point, its angular velocity is 0, right? The centripetal acceleration increases as it swings. Anyway, where was I? So basically, I take this and I solve for Fa, which is what I'm interested in, right? Just solve for this. And you get mg minus mat. Now, mat, right? How is that related to angular? Well, at, that's m L alpha. Remember, at is equal to, I guess which, am I talking, I guess the question though is which point on the rod am I talking about though, right? That kind of matters. There's this, if I write this, right? This would be the tangential acceleration for what? This is end of rod, right? Was I specific about which point I'm interested in? I mean, look at it. The tangential acceleration is different at different points of here as I let it go. First of all, the point where it's pivoting has 0 tangential acceleration, right? The point out here has much more. The point in the middle has half. So the question's ambiguous unless I said which point am I considering to find the tangential acceleration. Did I say that? So many words. Oh, I just said find Fa exerted on the pivot point. Huh. Oh, I think I have to consider the center of mass. So I should probably put L over 2 there, I suspect. Yep. So that would be at the end of the rod, but I have to use the center of mass concept, so I'm supposed to put L over 2 here. There we go. Yep.
How do you get to that from the mass times acceleration tangential equaling ml over 2 alpha from the one I thought about?
I didn't. This is just what's the relation between the tangential acceleration? It's the radius times the angular acceleration. This is the relation between angular and tangential acceleration, just generically for rotational motion. But in particular, we're interested in this center point here because that's where we're thinking of this particle as being a point, basically. I mean, I don't know. There's a lot to derive there. I'm just giving you a guide here. Let's see here. So anyway, you solve for FA, and that's the center of mass location for the radius, and then this is the angular acceleration we derived from the earlier part, and there you have it. It's 1/4 gravity, as it happens. That's a nice result, right? And I think if you play with some markers or a ruler or something for a little bit, you'll come to believe that. I mean, if you hold, it's kind of hard to judge. It seems to me like it's more than a 1/4 of the weight, but that's because the way I'm holding it. I don't know. It is what it is. I personally find this to be a difficult example. It's a lot to absorb. This example to me is easier, and also a typical test question. Suppose the blocks pictured are connected by a massive pulley with moment of inertia I and radius r. If the table is frictionless and the rope does not slip, find A and alpha. It's pretty straightforward problem. Basically, we look at Newton's second law and everything involved. Or you could use energy conservation. There's two different ways you could do it, right? If you use energy conservation, which would be reasonable because there's no friction, what you'd have to say is that the energy at any point in time of the system consists of what? What are the ways energy are stored in this mechanical system? Kinetic energy of M1, right? Potential energy of M1 is constant throughout, right? So we can just essentially ignore the potential. There's no change in the potential energy for M1. So we can choose a potential energy function for M1, which puts it to be 0 at the start and at the end. So let's just do that. So you got kinetic energy for M1. You've got the rotational kinetic energy of the pulley, 1/2 I omega squared, right? And then you have both the kinetic energy of M2 as well as the potential energy of M2, which in fact does have opportunity to change here, right? You take the sum of those 1, 2, 3, 4 energies, that's the net mechanical energy that has to be conserved, and you could conserve it to solve problems here, right? That's one way you could solve this kind of problem. The other way you could think about solving this sort of problem would be to study the dynamics, which is what I'm doing here. Like, what's Newton's second law on M2 rather? M2A is M2G, right, minus T2. That's just the Newton's second law on M2. Everybody with me? How about this one? On M1, you just have M1A is equal to T1. Now, T1 and T2 don't have to be equal because you have a massive pulley, right? So that there's torque there. For the pulley, we have rotational second law of I times alpha is equal to RT2 minus RT1, right? Because T2 is pulling, right? T2 is pulling a distance r from the pivot point, so that produces torque, RT2, and T1 is pulling distance r from the pivot point, that produces minus RT1, because I've taken, this is the positive alpha because that's the way downward is the way I've taken acceleration to be. You see, once I write this, I've just declared downward motion of M2 as positive. So to be consistent with that, I'm just following the signs. Are you guys with me here? So I alpha is sum of the torques. Does that make sense? Then the non-slip condition. Non-slip condition relates the angular acceleration and the the tangential acceleration. This is what you just asked me about this a second ago. Like, why was this guy true, you know? It's exactly that again. Radius times the angular acceleration gives me the tangential acceleration, the non-slip condition. And then you do algebra. And so what I typically do is I divide by r squared to make the rotational torque equation, rotational Newton's second law, to have the same units as Newton's regular second law, so I can add equations and junk. And I do that. And you do some algebra. And after a bit, you get these. I think I did this example before, didn't I? I'm sorry, I think I'm in reruns right now. I don't want that.
did the one with two masses.
Oh, I did the massive pulley Atwood machine. Is that right? Like the
Yeah.
yeah. Your stupid lab book would have us replace I with MEQ, and then wouldn't tell us about it.
Did that graph ever end up working out well, or?
The graph?
Yeah.
Yeah, Mr. Anderson. Where's Mr. Anderson? You got that graph to work within like 3 or 4%, right?
Yes, sir.
Yep. Can be done. The good thing is, since you guys are in my section, your lab grades will find a way to get curved at the end. It's funny how that works. Sorry to Miss Dromby's students. I have no such power. I guess if I asked her nicely, she might curve them. I don't know.
What about Dinsmore?
I have no such power. No, Dinsmore grades very carefully. Like his grade, he's been at this a while, and his 201, 202 courses, they're a well-oiled machine. He knows exactly which points are where, and like it is not. They got multiple choice tests, and points are points in there. There's really not a lot of curving going on in that class. Like it has been done for a while. It is what it is. You get what you get. It's not quite that way in here. Anyway, so suppose an engine makes a torque of 678 Newton meters at an angular velocity of 4,500 revolutions per minute. Find the power output. How many light bulbs, 100 watt, produce the equivalent energy output? These are actual 100 watt light bulbs, not some kind of asinine relabeling system that you find at stores where a 100 watt light bulb is actually a 10 watt light bulb that happens to be an LED light bulb. Because rather than educating people on what wattage actually means, or perhaps giving a more reasonable nomenclature for light manufacturing, like, shouldn't we talk about lumens?
I always look for lumens.
Yeah, lumens would be helpful. Like, if you see, incredible shop light, and then like you look at the lumens and it's like, I don't have a good sense of the numbers, but sometimes you'll see these.
15 is a candle.
Yeah, so you'll see like 15 is a candle, right? So I'm trying to think, what's that? 100? I know those 500 watt shop lights, like the halogen shop lights, there's something like 10,000 lumens or something, right? I mean, they're
They're big, they're bright.
yeah, you can like feel it, right?
Yeah.
And then you'll see like some little toy LED thing that'll have like, it's advertising itself. It's got like stands and stuff, right? It looks like it's the same thing as that. But when you actually look at the number of lumens and you notice like it's 1,000 as opposed to 10,000, you're like, come on. It's just cheating. But it's like effectively effective of, I don't know, the wattage effectiveness.
Don't
Like-
look at lumens for plant grow lights either.
For what? For plant
Grow lights?
plant grow lights. That doesn't seem like the sort of thing a Liberty student should be looking at.
I had a very nice indoor garden for my mother for Christmas. Thank you very much.
Indoor garden.
I cooked glass.
Indoor garden for your mother. Yes. Okay. I understand. This isn't Colorado, guys. Come on. You need to go to jail for that sort of thing. Anyway, so dw is FDS. A little bit of work done is the force over the displacement, right? This is also true for along like an arc. So if you rewrite that as d theta, you've got dw is the force times radius times d theta, which would be like the torque times d theta. You divide this thing by dt, you got dw dt is equal to tau d theta dt. In other words, the power developed by a work along a circular motion is the torque times the angular frequency. So long story short, if you're given a problem like this, where you're given the torque and you're also given the angular frequency, you multiply them. It gives you the power. Okay? Just like before, if you wanted the power developed by a force that was being applied to a particle with velocity v, F dot v gave you the power developed. All right? That's actually what we integrate to calculate the work done in the work integral. If you look at the thing we're integrating in the line integral for work, it's the power, it's the force dot the velocity. Anyway, you do the unit conversion, you get 319.4 kilowatts. Yay. Anything else I have to show you? Show and tell done? Maybe. Let me just go back and look at this one more second. La 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 la. Oh, there were examples back here. Example 4. Let me just kind of a whirlwind lightning round of examples here. Suppose you have 100 newtons applied to a wrench. What's the maximum torque you could place on a rusty belt? This is a trick question. It's impossible to answer this question unless you know how long a lever you have on hand, right? So, I mean, have you guys ever seen like truckers along the side of the road trying to take off one of the wheels from like a 18-wheeler or whatever? You ever seen the like tire iron they have? Right, the thing will be like, it's like 10 feet long sometimes, like an extender bar, and you'll see them like 8 feet away from the thing, like jumping on it, right? Because those are really, they have those like stupid air wrenches to put those things on, right? So in principle, if you had something like this, you could put a lot of torque on a bolt if you had a sufficiently long wrench, because the torque is equal to the radius arm times 100 newtons. As r goes to infinity, the torque goes to infinity. Woohoo! Right. Don't question the picture. Is he carrying a sphere? A sphere? What? A spear. Sure. Those are mechanics chopsticks. I don't know. What do you want from me? What do you want from me? All right, here we go. Example 5. How long a lever do you need to increase your applied force 100 times? All right, so, if you've got some sort of uneven teeter-totter, you can do that, right? So, like, the torque you apply here is R times F, right? The torque you produce over here is the output force times L. And those have to be equal, right? Why? Because torque is equal to 0 on the pivot point, right? So the sum of the torques, if this is in equilibrium, has to balance out. Whatever torque is here has to be matched by the torque there, right? I guess there's also the gravity. I'm ignoring the actual mass of the rod. Okay? Don't worry, we have a lab where you study the torque produced from the mass of the rod in addition to masses which are hanging on the rod. There's actually a lab about that we'll do soon. But not this week. Woo-hoo. Yeah, I had to cancel lab because we have this Math Geek award ceremony thing that we have to do, and I should actually go to it. Because as you know, while I am Mr. Cook in here, I'm Dr. Cook most of the time. So I should actually go to award ceremonies that happen once a year. So sorry to disappoint you guys and cancel lab. It saddens me so very deeply that we don't have lab this week. I'm dying inside even now. So, what's that? You can feel the emotion in my voice? That's good. I can feel a cough coming. That's what I feel. So you get something for nothing, right? You can increase your force by 100-fold just by having this, uneven teeter-totter. What's the rub? Yes, Travis? How does this work? How can you just multiply your force by 100? Doesn't that seem to suggest you get some kind of perpetual motion machine? You just get an uneven teeter-totter and you just push on one side, you can push more on the other side, and yep.
You get less distance out of it, so it's
Exactly. So this applied force has to go through more distance, which means you do the same work with a lesser force over a longer distance. Over here you get a smaller force, but a greater force, but a smaller distance. But energy is conserved, so the work it takes to apply is the same as the work you get out. It's not magic. Energy is conserved. It's just that the force is applied over a smaller distance as opposed to over a larger distance. Very good, very good. anyway, oh, the answer is 100 times because, as I explained. Now here's, and this is just explaining what I was just talking about. Like, so the difference is, if you think about that thing I was just talking about, you can see the distance is much further for the point which is farther away, right? For the same angular displacement, you get this little displacement over here, you get this big displacement over here. That's why we get a larger force over a smaller distance versus a smaller force over a larger distance. The work is equal, though. All right, I think I showed you this before. Yeah. One last example, and then I'll get back to gravity. I'll start gravity. So here we have, an example 2. Oh, fine. Sorry, my examples are out of order. It's kind of a harder example. I don't have much. This is the hardest example I'll show you in here. Find the torque on a cylinder of mass m and radius r if a small mass, little m, is attached to the rim of the cylinder, all right? So if you can imagine this, like, suppose you took like a coffee can or something, filled it full of cement so it's rigid, right? And then you attached like a, I don't know, like a big lead ball on the rim of it, and you let it rock back and forth. Like, what would happen? You can imagine, like, the motion would it would just sort of roll back and forth according to that little ball being sort of the break in symmetry, right? It would the little ball would roll a little bit up and then a little bit down, a little bit up. But the motion would be slowed because the big cylinder has to roll with it, right? Like, you can imagine this would roll. This wouldn't stay like that, right? If you put that in, it can roll, it would fall down, right? Eventually, if there's friction, this should come to rest with the little mg down here, right? Nature is lazy. It tends to the state of lowest energy if at all possible. Okay, that's a basic thing here. Anyway, so you look at the torque on the system, you have mg r cosine theta because that's the part of the gravity which is actually acting like this. Like this. So that's the part that's this. And mg, well, so there you go. That's the torque on the mg. And so torque is equal to I alpha. The inertia is coming from two things. One half mr squared, the inertia for the cylinder, and then mr squared because the little mass is all at radius r, all right? And so that's the torque equation. And if you look at that, what that actually gives you is this differential equation. I alpha would be, there's the I. Alpha is d squared theta dt squared. And the torque, well, that's mg r cosine theta. Well, this is a kind of interesting differential equation because it's nonlinear. So I've got like cosine theta and I've got d squared theta dt squared. Now, I've been talking to some subset of you about the importance of power series approximations. This is actually an example where we use it. We replace the cosine with this in principle, right? And if you just keep the first term, then you've got this differential equation. Where was I? But I don't want to do that. I want to solve it for sorry. So anyway, so if I just keep the constant term, then I get this equation, which I can integrate twice, and I get the tangential acceleration is minus 2 mg over m plus 2m. That's kind of interesting. If you let m equal to 0, right, then it would just be the boring coffee can full of cement, and it would just sit there. It wouldn't have any kind of torque at all. It would just sit there, right? This formula makes sense. If little m goes to 0, the tangential acceleration is 0. If, on the other hand, the mass of the coffee can goes to 0, then it would just be basically what? Just a mass that's free falling, I think. And if this m goes to 0, this will go to minus g if you study it. See that? If this is 0, then it's just minus 2 mg over 2m, which is just minus g, which makes perfect sense. So these limiting cases make a lot of sense. Now, skipping back ahead a little bit here. So I found this differential equation that describes the motion of like I said, a solid cylinder with a little mass attached to it. It's more interesting, perhaps, to expand cosine theta about 90 degrees. For those of you in my Calculus 2 section this morning, I talked a little bit about sometimes you want to approximate around somewhere other than 0 for a physical reason. Here's an example of that. It makes sense to, like, around 90 degrees. Well, that would be when the mass is, like, down here. So it's going to have a little rocking motion like that. And so around 90 degrees, cosine theta can be rewritten as theta plus pi over 2. All right? And, well, excuse me. Getting to the point, we have d theta dt squared, or something like minus this thing squared times theta plus pi over 2. You make a substitution, it gives you d squared y dt squared is minus wy. Anyway, getting past the math here, which I don't really expect you guys to do, obviously, since differential equations isn't a prerequisite for this course. I finally find my way to the angle minus pi over 2. I think I'm supposed to expand it around minus pi over 2. I've been saying pi over 2. I should have said minus pi over 2. Sorry about that. And then plus this thing, where the angular frequency of the motion is the square root of 2mg over r times m plus 2m. So you actually are able to, through through appropriate approximations, determine the frequency of oscillatory motion by just studying, like replacing a cosine or a sine with the power series for it, and you can work out the math. I mean, this is pretty well-known stuff. Now, your book doesn't have much on this, but we used to use an introductory book by an author named Tipler. Dr. Skambordis is seriously considering going back to that book because it's a much more intelligent book. This book you have is not a bad book. It's the book I learned from. My wife learned from it too. She self-studied in high school. It's a classic book. It's a great book. But it is missing some deeper discussions of these sorts of things, which would be appropriate for university students. Especially for you guys, because many of you aren't really freshmen. A lot of you are juniors or seniors because you put it off taking this course. By now you've had Diffie-Q, some of you. Show of hands, who's had Diffie-Q? Okay, just one. Sorry to single you out. But not so sorry. That I won't do it again. Let's see here. All right, well, that's all I got on angular momentum, you guys. So let's talk about gravity. So I've been lying to you. Well, not exactly lying, but just not telling you the truth. Well, as a point of philosophy in here, am I ever really telling you the truth? I mean, what's true? What's actual physical reality? I personally don't think any of the quote-unquote laws I tell you are laws in the sense of, like, is God good? Right? Can sin separate you from God? Will God keep his promises? Like, these are true things, right? Newton's law is an approximation. That's true in some certain circumstance, and I don't think this is any different. So Newton's general law of gravitation is this. F excuse me, is equal to, well, in magnitude, it's g m1 m2 over r squared. Now, that's the boring case. Let's say that puts m1 at the center, it puts m2 out here. The r is the distance that connects them, all right? In what direction does this force go? It's attractive, right? So we're talking about the force on M2. It's like this, right? This is the force of gravity produced by M1 on M2. In other words, this is the gravitational attraction of M1 on M2. It pulls M2 towards M1 along the line which connects them. These come in a third law pair. What's the force of gravity of M2 on M1? Same magnitude, but if I was to graph it, it would be like this, right? Force of M2 is gravity, let's say, exerted on M1, right? Yes, the Earth is pulling me down, right? And you, but guess what? We're also pulling back on the Earth. We are exerting a gravitational attraction on the Earth as well. It's just our mass is pretty tiny, so Earth doesn't really care. Right? I mean, that's roughly speaking the case. G is the universal gravitational constant. It is a big number. No, wait a minute. Opposite story. It's not a big number. In fact, there was a time in my life I had this memorized. Ah, there it is. 6.67259 times 10 to the minus 11. Now, you guys probably are fine if you just use the first 4 digits in that for most everything, you know? What are the units? What's that? No, there have to be units. I mean, it has to have a dimensional. I mean, this, I'm somehow multiplying masses and dividing by a length squared to get a force. So if you look at it, it has to have units of newtons, because that's what we want. But it better cancel out the meters squared, and it better cancel out the kilograms squared. Of course, you can simplify that, but I like to think of it like that.
What's the kilogram for?
If I'm multiplying by this and dividing by that, in order to make this work out to newtons, I have to like have a multiplication by length squared and then division by mass squared. Now, this is an experimentally determined quantity, all right? Now, this is the simplest formula. Now, like, what's a... this is not what I usually... I don't usually start with this formula and then I regret it, because students, I think, understand this formula pretty well, right? But what if you have a more complicated situation, or a less pretty situation, where you have, say, one mass, M1 here at R1, and you have another mass over here, say M2, at R2. Specifically, what's the vector formulation of gravity? What can we can be more precise here than this sloppy scalar formula in a picture. We can be much more precise. What we do is we think about the line which connects to these masses, like so, right? And so the distance between them we'll call script r. Script r is the magnitude of R2 minus R1. Let's see here, and then script r vector is what? If I call this, so suppose I call this, I can't draw it worth anything. Let's see, where is that in my picture? Script r plus R1 is equal to R2, right? So that means script r is going like this. This is the script r vector. It points from M1 to M2, as I have it set up at the moment. All right. Okay. So what's a unit vector in the script r direction? Looks like this, right? Agree? Okay, so what's the formula for Newton's universal law of gravitation in this nomenclature? It's just F is equal to minus G m1 m2 divided by script r squared and then script r hat. There you go. And I can put a vector on it now because it is, after all, a vector. There it is. Because this happens. Well, if it was plus, it would be like this. The minus says that the force of gravity, so what I'm telling you is the force of gravity, gravitation produced by m1 on m2, it looks like this, right? Next semester, we talk about electric forces, right? The formula is the same as this. You could have charge 1, charge 2, all right? In fact, guys, the reason I'm doing this, it's not so much that we need it for the gravity problems I'm going to solve for you primarily this semester. In fact, the bulk of them you can get away with doing very little with vectors. I'll show you in a second. But it is, after all, a vector force. But the other thing is, it's important to start trying to understand this formula because you must understand it next semester. It's a big part of it. 10% of your grade next semester is understanding this. At least 10%, maybe 20% of the grade next semester is just understanding this formula in the vector sense. Or next year, whenever it is you take it, I don't know. But when these are charges, right? Like charges repel, unlike charges attract, right? So if you replace this with like Q1, Q2, then if you get what? You get rid of the minus for one thing. Get rid of the minus, you just put Q1, Q2 here. Think about it. If there's plus and plus, you get a positive. If you get minus, minus, you get positive, so it's repulsive. If they're dissimilar, though, you produce the minus with unlike charges. But the formula is the same. It's called the Coulomb force. I'm getting ahead a bit. I won't test on that. So there you go. Anyway, a foreshadowing and possibly helpful comment. I don't know. We'll see. All right, so first things first, you know. You're on the Earth, mass of the Earth, right? And then there's us sitting up here, m. What's the force of gravity at the surface of the Earth? Well, so something like minus, well, let's just talk about magnitude, okay? Obviously, it's going towards the center of the Earth. I think we've established that even experimentally today, right? Yep. Never goes sideways, does it? Always straight down. Sorry. It amuses me. So we got G, m, mass of the Earth, divided by the radius of the Earth squared, roughly speaking, ignoring mountains and such, Death Valley, whatever. I mean, you could walk up to the top of the Vine Center. It wouldn't be much different. I mean, don't do that. But so the question then is, what are these values, right? Well, that's equal to ma, right? So we have what? We have the acceleration is g me.
Professor, when you say MA, what does that mean?
The mass of the person or whatever at this little m up here. So then you got to put some numbers in, right? So this is like 6 point, what did I just say, 6.67 times 10 to the minus 11, something like that. Mass of the Earth. Anybody happen to know mass of the Earth off the top of their head? Radius of the Earth is about 6 point. Oh, man. I mean, on the one hand, I'm happy I don't remember this because it means that I've misplaced that useless piece of information in my head with something more useful, possibly. But then I worry. What did I replace it with? You know, it could be some fun fact about Trump for all I know. I don't know. 6,378 times 10 to the 6th meters. Wowzers. You got to square that thing. And then, what would you comment?
Mass of the Earth is 5.972 times 10 to the 24th.
5.972 times 10 to the 24th, yeah. That's kilograms. All right, actually, so the masses, let me get rid of these pesky multipliers here. So the units work out to what? Meters per second squared, right? And this is approximately 9.8 meters per second squared, which we have talked about before, yes? But that's a specialization, right? If you were to somehow, you know, get in a spaceship and fly off towards the moon, eventually the force of gravity that Earth exerts on you would get smaller, right? And eventually tend to zero as you get further and further away, right? Right? We don't really feel, pragmatically speaking, even the gravitational pull of other planets, right? You're like, you don't look up at the night sky and go, man, I really feel Jupiter today, right? Or even the moon. I mean, I guess the moon has effect on the tides and such, right? So we observe it indirectly, the gravitational influence of the moon, but if you just, I mean, can you feel the pull, the gravitational pull of the moon? I can't, right? So, so that's first things first. What we've been doing before is we've been basically what we've been doing is saying, well, since we're always working where the, you know, basically r is essentially always equal to the radius of the Earth in previous problems, right? Previous work. So basically f is just equal to mg, right? But of course, you know, this is an approximation, right? And that's an approximation. Well, what else is an approximation? How about potential energy? MGH, that's also an approximation, right? If you look at, you know, F equal to G M E, right, divided by R squared, if this is going to be equal to minus du dr, because it's essentially just one-dimensional, right? Oh, sorry. Yeah, that's fine. That's fine. Although, I guess technically I got a minus here, right? And I'm talking about the radial component of the force.
That.
U, potential energy. Like potential energy, if you want. What have we called it before? I can't remember. What was my symbol for potential energy in here?
U.
Oh, okay. Well then,
That
oh.
or
Or PE. What happens if you integrate this? What's the integral of 1 over r squared? Minus 1 over r squared, actually. It's that, right? Although, what I need a minus, though, right? The minuses cancel over there. Integral of 1 over r squared is minus 1 over r. Plus a constant, right? So if I just don't put a constant, I'm setting u of infinity equals to 0. That's a normalization you can choose. That's a place you can set the 0 to be. And there you go. This is the potential energy where this is potential energy that you should use if you're answering questions that involve masses which are not all at the surface of the Earth, right? If you want to answer a question about like motion that involves gravity, and it also involves like things things not all at the surface of the Earth, this is what you need to use. If you use MGH, it just isn't true. Okay? So I suppose I could set this plus a constant, right? If I set this equal to plus a constant, then u of what? U of the radius of the Earth would be what? I guess, excuse me, let me talk about this a different way. Let me forget the constant for a second. Suppose I stick with my original formula, which is what I usually use. What happens when you plug in radius of the Earth? What do you get? You get this, right? If you use this formula, what you're saying is that potential energy due to gravity, where we are right now, is negative, right? And what is the energy? Minus GMM ME over RE. That's the energy level we're at right now. If you set the potential energy to be 0 at infinity for this one. So you can draw a graph of what's going on here. Here's radius. Here's the potential energy diagram, right? And where we are, our energy level is minus G MME over RE, right? If you want to escape the gravitational attraction of the Earth, you need a certain amount of energy to break this bond, right? If you have more kinetic energy than this, you're free. Right? So there's a certain velocity that will no longer make you gravitationally bound to the Earth. Escape velocity, right? All right, I'm going to shut up about that. Let's work another example. So this one, we're actually going to put some things together. You got the sun. All right. And let's talk about the Earth. And to a relatively decent approximation, the motion is what? Elliptical. Spherical. Elliptical is correct, but I was looking for circular. But this is kind of neither. I was trying for circular, but I failed. To a decent approximation, the motion's circular, all right? Again, a lie, but a useful one. I mean, and it's an approximation, it's not a lie. All right, so fine. What I'm about to show you is so simple. So how do we relate? So supposing circular motion, right? You have a radius, right? It's going in basically a circle. There's some velocity, right? That the Earth has. And why does the Earth continue to rotate around the sun like this? What's keeping it rotating? What's it doing? Right, it's falling around the sun, you could say, right? It's gravity, right? What's the direction of the gravitational force of the sun on the Earth? Inward, right? So if I was to draw that here, it would look like this, right? G, mass of the Earth, mass of the sun, divided by this r squared, right? That's the force of gravity. It's going in a circle. What did we derive like the first week using calculus? M, mass of the Earth. Let's draw Newton's second law on the Earth, right? The mass of the Earth times the velocity squared divided by what? The radius, mv squared over r, has to be equal to the net force, right? Well, in this case, there's no